Welcome to the Deep Dive, your shortcut to being genuinely well-informed with just enough humor to keep things interesting. Think about it, so much of our world runs on batteries. Your phone, maybe your car. But what's actually going on inside? What keeps them running safely, efficiently, reliably? Today, we're taking a deep dive into battery management systems, BMS for short. These are really the unsung heroes, kind of the hidden brains orchestrating everything inside a battery pack. We've gathered a lot of technical info, almost like a blueprint of how these critical systems work. Our mission, to unpack the jargon, figure out what a BMS really does, and explore the clever ways it keeps batteries performing well and, crucially, safely. We want to turn the complex stuff into something clear for you. Okay, let's unpack this. So to really get a handle on what a BMS does, it probably helps to refresh some basics about batteries themselves, right? We don't need a full physics lecture, but maybe some key ideas the BMS is always dealing with.
Exactly, yeah. The fundamentals are important. So first off, you've got energy and power. Energy, that's the capacity to do work measured in joules, or more practically for batteries, watt hours. Like your EV might have a 60 kilowatt hour battery. 60 kilowatt hour power, though, That's different. It's how fast you can use that energy, measured in watts. Think of it like energy is the amount of fuel in the tank. Power is how fast the engine can burn it.
Fuel amount versus burn rate, got it.
Then there's capacity. That's the total charge a battery stores, usually in ampere hours. So 100 battery could theoretically give you 100 amps for an hour. It's a really core number the BMS tracks. And the total energy is just that capacity multiplied by the battery's voltage. Simple relationship. Energy, capacity, F voltage.
Right. So we know how much it holds. But you mentioned how fast that speed of charging or discharging sounds really critical too.
Oh, absolutely critical. That brings us to the C rate. It's basically a measure of charge or discharge speed relative to the battery's max capacity. So a 1 C rate means, like I said, full discharge in 1 hour. A 0.5 C rate takes 2 hours. But push it to 2 C. You empty it in just 30 minutes.
Wow, okay.
And this C rate, it's not just academic. It dictates, well, everything about how the battery can be used safely. Pushing it too hard without a BMS stepping in, that's asking for trouble. It's one of the first things the BMS watches.
That makes a lot of sense. So the BMS isn't just looking at one number, it's juggling multiple things to figure out the battery's condition in real time. How does it actually measure, how full it is or how healthy it is?
Yeah, it uses several key indicators to build that picture. First, there's open circuit voltage, OCV. That's the voltage when the battery's just sitting there resting, no load, no charger. When it's properly rested, the OCV gives a pretty decent clue about its state of charge, the SOC.
Okay, resting voltage.
Right. Now, compare that to closed circuit voltage, CCV. That's the voltage while current is flowing. CCV is always changing. It drops during discharge, goes up during charge. That's because of the internal resistance inside the battery.
Ah, okay.
So then we get to these states the BMS calculates. State of charge, SOC, that's the easy one, remaining energy as a percentage, 50% NANOC, half full. Depth of discharge, DOD, is just the opposite. How much energy you've taken out. So if you use, say, 6 kilowatts from a 24 kilowatt hour pack, that's 25% DOD, which leaves you at 75% ASOC.
Got it. SOC and DOD are flip sides.
Exactly. Then there's state of health, SOH. This one's super important. It compares the battery's current maximum capacity to what it was when it was brand new. A new battery is 100% SOH, but they degrade, right?
Right, like phone batteries after a couple of years.
Precisely. And that leaves to remaining useful life, or RUL. That's the estimate time for charge cycles before the battery hits its end of life. Often that's defined as, say, 80% of its original capacity.
So SOH is how good is it now? RUL is how much longer will it last?
You got it. And we also track state of power. SOP, the max power it can safely handle right now, in or out.
Yeah.
And state of resistance, SOR, its internal resistance. Higher resistance means more energy wasted as heat, less efficient power delivery. So the BMS watches that closely too.
It really sounds like the BMS is tracking the battery's entire life story from day one until retirement. How does it monitor that whole journey, including, how it gets charged up?
Yeah, it's a continuous monitoring job. It looks at things like discharge curves, graphs of voltage versus capacity as it drains. Flatter curves usually mean better, more stable performance. Cycle life is another big one, just how many charge-discharge cycles it can handle before hitting that end of life, that 80% OH or whatever the marker is. Batteries also have this thing called self-discharge. They just lose a bit of charge over time, even doing nothing, like a tiny energy leak.
A parasitic drain. Okay.
Yeah, right. And then there's the overall degradation. Capacity just fades with time and use, especially if you repeatedly drain it really deep and charge it back up. That accelerates aging. The BMS tracks this whole process from BOL, beginning of life, to EOL, end of life. EOL might be defined as like 80% of BOL capacity, or maybe a 50% increase in internal resistance. Depends on the application.
And the charging part, how does the BMS manage that?
Charging. Usually two main phases. First is constant current, or CC. The BMS tells the charger to push in a steady current. The voltage climbs gradually, taking the battery from maybe empty up to around 80% SOC pretty quickly. That's the fast part.
Okay, CC for speed up to 80%.
Exactly. Then around 80%, it switches to constant voltage, or CV. Now the BMS holds the voltage steady at the target level, and the current naturally tapers off as the battery gets full. This gently tops it off to 100% without overcharging or stressing the cells. It's crucial for safety and longevity.
Wow, that is a lot of dynamic data for one system to manage. So, okay, stepping back, what is this BMS fundamentally? Why is it so vital everywhere now?
Right. So at its heart, a battery management system, the BMS, it's an embedded electronic system. Think of it as the brain and nervous system for a rechargeable battery pack, especially crucial for lithium-ion, lithium polymer, the high-energy ones. Its core job, keep the battery operating safely, reliably, and efficiently. It's absolutely essential in high-voltage systems, EVs, grid storage, even powerful laptops or medical devices.
So yeah, definitely the battery's brain and bodyguard rolled into one. Now, with all those things, it needs to track and control. What are the main jobs it has to do? This is where it gets really interesting.
Absolutely. We can break it down into about 5 core functions. First, pretty obviously, is monitoring. It's constantly measuring everything: voltage, not just the whole pack, but each individual cell, current flowing in and out, and temperature, often in multiple spots because heat is the enemy. Avoiding thermal runaway is priority number 1.
Can't have fires.
No. And it's also continuously estimating those states. We talked about SOC, SOH, SOP, and SOE, which is state of energy or remaining energy.
Okay, monitoring is job 1. What's next?
Job 2 is protection. This is the bodyguard part. It actively prevents the battery from going outside its safe operating limits. So things like overvoltage, undervoltage again, per cell, and for the whole pack, overcurrent. Temperatures too high or too low. It also looks for short circuits, ground faults, major electrical safety hazards. If it spots danger, bam, you can cut off the power, limit the current, whatever's needed to keep things safe.
Okay, vital. Monitoring and protection. What's third?
Third is cell balancing. This one's super important, but maybe less obvious. Think about a big EV battery pack, hundreds, maybe thousands of individual cells. Even with amazing manufacturing, no two cells are perfectly identical. Tiny differences in resistance, how they age, maybe one gets slightly warmer than another. Over time, these little differences cause the cells to get out of sync. Some charge faster, some discharge faster, their voltages drift apart.
And that's bad
Because the whole pack's performance is limited by the weakest cell. If one cell hits empty first, the whole pack stops discharging. If one hits full first, the whole pack stops charging. You lose usable energy, and worse, you can damage cells by pushing them too far, overcharging the strong ones or over-discharging the weak ones.
Okay. It's like a chain is only as strong as its weakest link.
Precisely. So cell balancing is the BMS's way of equalizing the voltages across all the cells, bringing them back into line so the whole pack works together efficiently and safely.
Okay, that makes total sense. How does it actually do that balancing? I think there are a couple of main ways.
Yeah, 2 main approaches. The simpler one is passive cell balancing. The idea here is basically to burn off excess energy from the cells that have a higher voltage. It does this using small resistors. When the BMS sees a cell's voltage get too high compared to the others, say it hits 4.21 volts, when the target's 4.20, it switches on a resistor connected just to that cell.
Okay.
That resistor draws a small current, acting like a tiny heater, and bleeds off energy until that cell's voltage drops back in line. Components are simple resistors, little MOSFET switches, control logic. It's cheap, reliable.
Where would you see this used?
You find it in lower cost applications, e-bikes, scooters, maybe some budget EVs, places where energy efficiency isn't the absolute top priority and the pack sizes aren't enormous.
Makes sense. What are the downsides then?
Well, the biggest one is you're just wasting energy as heat, literally burning it off. It also generates heat itself, which the system might need to manage. And it's pretty slow, especially for large capacity cells. It can only bleed off a small current.
Right, so not ideal for high performance or big batteries. What's the alternative?
The alternative is active cell balancing. This is much smarter, much more efficient. Instead of wasting energy, active balancing actually moves energy. It takes charge from the higher voltage cells and transfers it to the lower voltage cells.
Oh, interesting, like Robin Hood for electrons.
Yeah, kind of. It redistributes the wealth. There are different ways to do it, using capacitors to shuttle charge back and forth, or inductors and transformers, sometimes even small bidirectional DC-DC converters. So in that high-performance EV pack, if one cell's at 4.22V and another's down at 4.15V, the active balancer efficiently moves charge between them. No significant waste heat.
Okay, that sounds way better.
It is, in terms of efficiency and speed. It can balance much faster and helps reduce cell mismatch over the battery's whole life. The downsides: it's way more complex. More components, capacitors, inductors, bidirectional switches, sophisticated controller ICs, so it costs more. And the switching involved can create electrical noise, EMI, that needs careful management.
And where do we see active balancing?
Definitely in high-performance EVs, think Tesla, Porsche Taycan. Also in large battery packs, like grid storage systems, or where maximizing usable capacity and lifespan is critical, sometimes even used between different modules within a giant pack.
Okay, monitoring, protection, balancing. What else does the BMS do?
Fourth is communication. The BMS isn't isolated, right? It needs to talk to the rest of the vehicle or device. It uses standard communication protocols, things like CAN bus, which is common in cars, or UART, SPI, I2C. It sends key info SOC, temperature warnings, any fault codes to the main vehicle controller, the ECU, the charger, the dashboard display, you name it.
Constant chatter to keep everything informed. And the last one?
The fifth function is logging and diagnostics.
Yeah.
Super important for reliability and maintenance. The BMS keeps a record of faults, errors, unusual conditions, key performance data over time. This allows for real-time diagnostics if something goes wrong, helps engineers understand how the battery is aging, and even allows for firmware updates over the air to improve performance or fix bugs.
It really is a complete little computer system dedicated to the battery. But going back to those states for a second, like state of charge, how does the BMS know? With voltage changing, current flowing, temperature shifting, how does it estimate SOC accurately?
Yes, the estimation challenge. It's tricky. There are two main techniques, and usually good BMS uses both together. The first is Coulomb counting, or ampere-hour counting. The basic idea is pretty simple. You measure all the current going into the battery during charging and all the current going out during discharging, and you integrate that over time. It's like keeping a running tally. If you know where you started, initial SOC, and you track everything going in and out, you should know how much charge is left.
Okay, like balancing a checkbook for charge.
Exactly. To do it well, though, you need really accurate current sensors, like a shunt resistor or a Hall effect sensor, a good analog-to-digital converter, ADC, to read it precisely, and an accurate clock. So if your 60 EV battery starts at, say, 90% SOC, and you draw 30 amps constantly for 1 hour, well, 30 amps times 1 hour is 30 ampere hours. The BMS subtracts that from the starting point and estimates the SOC is now down to 40%.
Seems straightforward enough. What's the catch?
The catch is drift. Accumulating errors over time. Tiny errors in the current sensor reading, tiny errors in the time integration, maybe not perfectly accounting for self-discharge or how capacity changes with temperature or age. These errors add up.
So the checkbook balance slowly gets off.
Precisely. Your estimate drifts away from the true SOC over time. So, Coulomb counting is great for tracking changes in real time. It's responsive, but it needs to be recalibrated periodically. In good automotive BMS systems, they do clever things. Use temperature-compensated capacity models and often combine it with sophisticated filters, like a Kalman filter.
A Kalman filter? Sounds complex.
It is, a bit. Think of it like a smart predictive algorithm. It takes the noisy measurements from the sensors, combines them with a mathematical model of how the battery should behave, and gives a much smoother, more accurate estimate of the true state, correcting for that drift along the way.
Okay, so Coulomb counting is this dynamic tracker, but it needs help. What's the other method, the recalibration part?
That's the open circuit voltage method, or OCV method. This relies on the fact that for a given battery chemistry, there's a known, fairly stable relationship between its voltage when it's fully rested and its state of charge. There's usually an OCD-SOC curve, like a lookup table, stored in the BMS memory.
So you let the battery rest.
Exactly. You need a relaxation period. Could be 30 minutes, could be several hours, depends on the chemistry and temperature. Enough time for the internal electrochemical stuff to settle down and the voltage to stabilize at its true OCV. The BMS measures that stable voltage, looks it up on the curve, and gets an SOC estimate. SOC gives a function of OCV.
Like taking its temperature when it's calm.
A good analogy. So if that 96-cell EV pack rests overnight and the BMS measures a stable 3.85 volts per cell, it checks its lookup table, maybe adjusted for temperature, and finds that corresponds to, say, 60% SOC. This reading is gold for recalibrating the Coulomb counter. It gives it a known, accurate starting point again.
Okay, so OCV is the anchor point. Why not just use OCV all the time then?
The limitations. Big ones.
Yeah.
First, that relaxation time. You can't stop driving for an hour every time you want an SOC update, right?
No, definitely not.
Second, OCV itself changes with temperature, so you need accurate temperature compensation. Third, the curve changes as the battery ages, so the BMS needs to adapt or update the curve. And maybe the biggest issue for lithium-ion. The OCV curve is often very flat in the middle range of SOC, so between 30% and 80%.
Flat.
Meaning a small change in voltage corresponds to a large change in SOC or vice versa. It's hard to tell the difference between 50% and 60% SOC just by looking at the OCV in that flat region. It's just not precise enough there.
Got it. So OCV is great for calibration when resting, but not for continuous tracking, especially mid-charge.
Exactly. So in practice, no modern BMS relies solely on OCV. It's almost always used in combination with Coulomb counting. Coulomb counting handles the minute-to-minute changes, and OCV provides periodic, accurate corrections when the system is idle.
So the real magic is using both methods together, playing to their strengths. That's clever engineering. But okay, we're talking about managing huge amounts of energy, complex electronics. Safety has got to be absolutely paramount. What does all this mean for us, the users? How are we kept safe?
It means everything. Safety is woven into the BMS from the ground up. It has to meet incredibly strict standards. We're talking both electrical safety, preventing shocks, fires from shorts, etc., and functional safety.
Functional safety, what's that exactly?
Functional safety is about ensuring the system behaves correctly and safely. Even if something goes wrong, like a sensor fails or there's a software bug. It's about preventing hazards caused by the system itself malfunctioning. For cars, the big standard is ISO 26262. It defines a whole safety lifecycle for electrical and electronic systems. It applies to the BMS hardware, the software, how it's all integrated. It mandates things like doing rigorous hazard analysis, defining clear safety goals, building in fault detection, redundancy, using tools like FMEA failure modes and effects analysis to systematically think through what could fail and how to prevent it or mitigate the consequences.
Okay, a very structured approach to preventing problems.
Extremely structured. Under ISO 26262, different safety functions get assigned an ASIL, automotive safety integrity level. It goes from ASIL A, lowest risk, up to ASIL D, highest risk. Critical BMS functions, like detecting an overvoltage condition that could lead to fire. That's typically ASIL D. Temperature monitoring might be ASIL C. The level dictates how rigorous the design, testing, and validation have to be.
So the really critical safety functions get the most scrutiny.
Absolutely. And while ISO 26262 is for cars, there's a parent standard, IEC 61508, that covers functional safety more broadly for industrial systems, which applies to things like stationary battery storage.
And are there standards just for the batteries themselves?
Oh, yes. Lots of them. Standards like UL 2580 for EV batteries in the US or UL 1973 for stationary batteries. IEC 62133 is a big one globally for portable batteries. These define specific tests. The battery pack and its BMS must pass brutal tests, actually. Short circuits, overcharging, over-discharging, crushing the battery, puncturing it, exposing it to extreme heat, checking fire containment.
Wow, they really put them through the ringer.
They have to. So all these standards, functional safety like ISO 26262 and battery-specific safety like UL, they completely shape how a BMS is designed. It dictates the software architecture needing watchdogs, robust error handling. It drives hardware choices, maybe needing dual temperature sensors for redundancy or separate pathways for measuring voltage. It requires comprehensive diagnostics and fault logging. Often a BMS and the battery system need third-party certification against these standards before they can be sold. If we connect this to the bigger picture, it's clear that these safety standards are absolutely fundamental. They're what allow us to trust this technology, what enables the widespread adoption of EVs and large-scale energy storage. Without them, and without the BMS enforcing them, it just wouldn't be feasible.
What an incredible journey. We've gone from the basic units of energy like joules and ampere hours all the way through the complex balancing acts and estimation algorithms inside the BMS and landed on these critical safety standards that underpin everything. It really gives you a whole new appreciation for that silent, complex system working away inside your EV or even your phone, keeping things safe and making sure you get the power you need.
It really does. And it raises an important question, too, looking forward. As we keep demanding more from our batteries, more power, faster charging, longer life, how does the BMS need to keep evolving? How will that ingenuity continue to push the boundaries of performance while still maintaining that uncompromising safety and efficiency?
That is a fantastic question to ponder. The innovation certainly isn't stopping here. Thank you for joining us on this deep dive into the world of battery management systems. Keep exploring, keep learning, and we'll catch you on the next one.